Now we are discussing about bias and variance. We are taking the same data in the three diagrams you are observing here. On x-axis, I am taking one feature x1. On y-axis, I am taking another feature x2. So this graph is the comparison of x1 and x2. And whenever you are seeing x here, that is representing y equal to 1. Whenever you are seeing circle here, that is representing y equal to 0. The line here I have drawn is a classifier. This is a classifier. The semicircle here I have drawn is a classifier. This curve, some different shape, it is also classifier. So we have used three classifiers. What is this classifier? This classifier is separating the data y equal to 1 and y equal to 0. Remember this linear classifier in the first case, above this straight line, all the training samples are, we are expecting all the output of all the training samples equal to 1. And below this straight line, we are expecting the output of all these training samples is 0. But in reality, that is not happening. You observe here. Below this line, there are many x. Nearly 3, 4, many x values means many ones are available. So we are calling this as underfitting, means this classifier is not properly fitting the data. And this underfitting problem we are addressing is called high bias. Whenever a person takes a particular decision in keeping with respect to his friend or relative without transparency, then we will say he is very high biased person, means he takes the decision that is completely favorable to his friend or his relatives. In that case, we use the term high bias. Here also, this classifier is not dividing the data y equal to 1 and y equal to 0 properly. That's why we are calling it as a high bias condition. We are now looking the third example. In this third example, this classifier has divided the data properly. Means above this classifier, everything is 1 only. And below this classifier, everything is 0 only. So we will say this classifier has almost 0 training set error, because this classifier is dividing the training set outputs y equal to 1 and y equal to 0 properly. But the question is, we are designing this classifier to predict the future values. If I ask any new sample, if I give any new sample, if I give some new sample, some training sample, some new training sample, can this classifier predict that value? No. Why no? Because this classifier does not have any shape at all. It is a random shape. So we will call it as a overfitting problem. It is fitting our data, but the concept here we are using, it is overfitting the data, means it is having high variance. So as of now, we discussed, whenever in the training samples itself, if we are observing the error, then it is a high bias problem. Whenever in the training samples, there are, the training set error is very small. But when we are giving you new samples, maybe in cross validation set, maybe in the test set, if we give the new training sample, or if we give a new input, then the problem comes. Then this classifier fails to predict the output. That's why we call this as high variance problem. Whereas this second example, you can observe here, almost this class, above this classifier everything is 1 except one sample, and below this classifier everything is 0 except one sample. We can accept that kind of error, because now this classifier is like a semicircle, or this classifier is like a parabola. It has a we have the capability to extend this classifier. because this curve is having proper shape and we can extend this. But whereas in the third example, this curve does not have any proper shape. It is a random curve, arbitrary curve. It does not have the capability to predict the future values. But in the second example, the classifier has the capability to predict the future examples. So that's why we call this as low bias and low variance problem. Means training set error is small and crash validation set error is small. Now we have taken one image. In the first image, we want to know whether in this image cat is there or not. If cat is there in this image, then y equal to 1. Yes, in the first image cat is there, y equal to 1. In second image cat is not there, it is dog, so y equal to 0. Now we have given many training samples like this. So in the first example, we have given the data and we observe why again we are dealing with error and like this concept. We will discuss. Remember here, these graphs I have drawn for the two features x1 and x2. But in real time, we don't have only two features for the input training samples. We may have some 10 input features for every training samples. We may have 50 input features or 100 input features or 1000 input features. We cannot draw all the input features by using this, because we can draw only a two-dimensional diagram or three-dimensional diagram. It is not possible to say whether the data is overfitted or underfitted, or whether the data is having high bias problem or high variance problem by seeing, because two-dimensional in the graph we cannot use all the features. So by seeing into the graph and telling whether the data is having high bias, whether high bias problem or low bias problem or high variance problem, it is not a convenience method for all. So we are discussing a new method. In that, we are saying if the training set error is very small and our crash validation set or development set error is very high, then we are saying it is having high variance. So the problem is high variance. Why high variance? Because the data is fitting for training set, but means the classifier or the neural network you have designed is fitting for training set, but it is not fitting for our cross validation set. That's why it is having high variance. In the second example, in the training set itself, we are having huge amount of error, but in the development set only we are having 1% error. Why 1%? 15% here, 1% here, so total error 16%. Now we are saying this is a high bias problem. Why high bias problem? Because in the training set error is more, and in the cross validation set or development set the error is very small. That's why it is a high bias problem. Whereas we are taking some more two examples. In the third example, we are having high error in the training set and high error in the development set. That's why we are calling it as a both high bias problem and high variance problem. In the fourth example, the training set error is 0.5 and crash validation set or development set error is only 1%. So it is a low bias problem and low variance problem. This is what we are really expecting. We expect we expect the bias should be low and the variance should be low if our classifier has to predict the proper output. And sometime you remember, in every example here we are expecting if a human being sees the image and he can predict whether the cat is there in that image or not. So Bayes' error is 0. If you give a blurred image, which human being himself cannot tell whether the cat is there in that picture or not, if you give it to the learning algorithm, then the learning algorithm shows, if it shows 15% error, we cannot say it is having high bias, because in the image itself the blurredness is there. So we will say the Bayes error in that blurred image is 15%. So the training set error, if it shows the 15%, it does not mean in that case that it is a high bias problem. Okay, that's we will discuss later. As of now, whenever you are seeing a high percentage of error in the training set, then this is a high bias problem. When you see high percentage of error in the development set, then it is a high variance problem. Now, already we have observed high bias problem, high variance problem in the machine learning. How can a high bias and high variance problem is possible? Now we are discussing about this. In this diagram, observe here, this diagram is drawn between x1 and x2 features. So if my classifier is like this, you can observe it is having high variance, because the classifier itself is like a not a normal, it is having normal shape, it is some having arbitrary shape, it is having high variance, and the total data is not at all fitted, means above the classifier we should get ones, and below the classifier we should get zeros, but that is not happening here. Below the classifier we are having many ones, so it is having high bias problem and it is having high variance problem. This is how we can represent the high bias and high variance problem on a graph for two features. So in machine learning, first we have to check whether in machine learning and also in the deep learning problems now, because which is a subset of machine learning, we have to check whether in this problem first high bias is there or not. If high bias is not there, means the training set error is very small, then there is no problem. If high bias is there, means the training set error is more, then what steps we have to take to make it as a low bias? First we have to increase the number of layers in the network. Neural network, deep neural network, if it is having example n layers, we should increase the layers more than n. And also it is possible by changing the neural network architecture also, we can decrement the bias. Suppose if the problem is not having high bias, then we will check whether it is having high variance or not. If it is having high variance, how we will check whether it is having high variance or not? By using the data set performance. If the cross validation set or a development data set, means if the development set error or cross validation set error is more and the training set error is small, then we are saying it is having only high variance problem. So now, how to overcome this high variance problem? By giving more number of training samples. If you do not have more number of training samples, already you have given all the training samples, then you can apply the regularization, or by changing the neural network architecture sometimes we can decrement the high variance. If you are not having high variance, then your neural network is ready, your neural network is having low variance and low bias, now it is ready to predict the output properly. In previous times, there is a concept called bias and variance trade-off, means whenever we are trying to decrement the bias, at that time variance is increasing. Whenever we are trying to decrement the variance, at that time bias is incrementing. I think you had in machine learning, whenever you want to decrement the bias, then to decrement the bias we have to take more number of features, but by taking the more number of features will increment the variance. Whenever we are taking the more number of training examples, that will decrement the variance, but that will because the training examples are becoming more, that may increment the bias. So but that is not at all a problem now. The bias variance trade-off is not a problem now, because we are using sophisticated processes. At a time we can decrease the bias and variance simultaneously by taking a large neural network with huge amount of data. By taking a large neural network, huge amount of data is the solution for a when we want to get a low variance and a low bias. network. This is how we have to take care. After the in the crash validation set only, we will come to know whether the neural network we have designed is having high variance or not. But in the training set error, we will come to know whether the neural network we have designed is having high bias or not. But the variance can be known only in the crash validation set only.